So next speaker is Professor Hongwei Zhang from Iowa State University. He will give us a talk about end-to-end open source ORAN prototyping in agriculture and rural communities. So Professor Hongwei Zhang is an electrical and computer engineering professor at Iowa State University. He leads the Center for Wireless Communications and Innovation and the Dependable Networking and Computing team at Iowa State. So.
All right, thank you. Good morning, everyone. It's a truly a pleasure and honor to be part of this celebration. Before I start, I just want to say that my first time actually touching OpenAirInterface, that was about 2019 when you folks organized the first North America workshop. We had a project that's where we started trying to push OpenAirInterface to the field, to the farm, right? There was a lot of uncertainty at our end when we started with that. But it's great that as of today, I think with the help of Florian and other colleagues at Eurocon, we were able to fully operationalize OAI and actually function pretty robustly nowadays in the field, which I will briefly touch upon. Thank you for that. So here, I will try to first give a brief introduction about one of the power platforms, the Era, that has a sharp focus on agriculture. And then I'll probably share an open call for contribution or participation about bringing, use OpenAirInterface to drive some of the low latency use cases and also the wireless innovations. So as folks who may have heard me talk about ERA, so it's designed to address the rural broadband challenge. So as we all know, rural broadband is a major society challenge today. And at least in the US, right, in the past decades, there have been billions of dollars investment into this, but most of those was focused on subsidies without looking at rural-focused technology innovation. So the key for ERA is to look at the unique technologies that can be used for agriculture and rural settings where the traffic patterns and the deployment scenarios are quite different. Also, the economics are so different. In fact, if you have paid attention to what's available, what the needs are, what opportunities are there in the rural regions in general, pretty much you can, if you look at this two-dimensional space of latency and throughput, you can find different kind of use cases from low-rate applications to high-rate, low-latency applications and so on. And in fact, some of the advanced applications can be best tried out in the open farm field, right? For example, think about low-latency automation of area and ground vehicles for agriculture automation. So with those in mind, ERA has been designed to capture those unique real-world rural context in terms of not just technology but also the deployment, operation, applications, and also economics. Look at how can you develop, try out new solutions that can reduce the rural broadband cost by a factor of 10 or more. And also, as we develop the Living Lab, there's a sharp focus about how to enable wireless and application co-evolution. So it's important to be able to drive wireless innovation, but be able to also tie that with the real-world needs of agriculture. So this does actually pose some challenges in terms of, programmability, performance, and robustness and heterogeneity. Right? It's actually oftentimes it's hard to accomplish all of this in the same setup. So at a high level, ERA has two layers of solutions that's being tried out. One is what you call the ERA Hall. It's this high-capacity wireless mesh you see on this map that was deployed around Ames, surrounding communities, and so on. And then at each of those sites, we're also deploying 5G and beyond access networks that can be used to connect tractors, sensors into the edge and cloud resources. There's actually research farms, producer farms, also actually to airports for folks who may love drones. This is where you can run a lot of serious actually drone applications. Just a little bit into the technology for the X-Hall, this is where you can find a diverse set of solutions that's operating all the way from the free space optical at 194 terahertz all the way down to E-band microwave, like E-band 80 gigahertz to 11 gigahertz. Also, there's a new backhaul that was featured. For the access network, we have both commercial grade Ericsson 5G platform, but also fully programmable SDR systems, and then somewhere in between the programmable low-band massive MIMO solutions. Again, there's actually from low-band, mid-band to high-band, there's a huge diversity there to support the diverse use cases, and also allow us to experiment with, think about how to leverage those different diversity, like spectral, temporal, and spatial diversity to improve robustness while accomplishing high capacity at the same time. There's a compute resources that's embedded end-to-end from user equipment to base station to the data center. We're also being connected with the national cloud infrastructures in US. And also, given the focus on time-sensitive networking and applications, there's actually end-to-end time sync, PTP running from the data center to the edge, and also the GPS-based synchronization of UEs. So in terms of actual where we are, so we have finished the phase 1 deployment at 4 sites you see here last year. And in those sites, we have both XHAL access network deployment, but also the deployment of state-of-the-art weather sensors, so they can detect fine-grained weather information and relate that to the wireless channel behaviors. And then we just finished the phase 2 deployment. As we speak today, actually, we finished the base station. Now we're kind of moving on to the UE deployment into the additional sites that you see here. So in terms of UE sites, you can find UEs in like crop farms, livestock farms, in those big ag vehicles, as well as robots used for crop sensing, for health monitoring of livestock. Also some of the bigger, more versatile robots. And also we had just started some joint effort putting radios and so on. Also some of the state-of-the-art farm facility like the feed mill bioprocessing plant, so you can get to experiment system behavior, understand system behavior in such more kind of industrial network settings. We're also working with the city, look at safe water, public safety, smart transit, and also like portable traffic control, residential deployment. Overall, with the current deployment of phase 1 and 2, we have about 7 base stations and close to 54 UEs that's going to be either operational already or to be deployed very soon in this large space of about 42 kilometer by 30 kilometer area. And so we have done actually some preliminary measurement so far observed for the commercial systems up to 3+ gig Bps wireless access throughput. Also, in terms of some of the low band radio coverage, we have been able to get to up to about 10 miles actually cell radius with good capacity. For the XHAL, about over 10 gig up to about 100 gig capacity. With those, we were able to try out really interesting agriculture applications that actually tend to require high data throughput and low latency. Also, we started some trials of 360-degree video streaming with some of the transport layer innovations. But one thing that's actually still open, we feel that cannot be fully supported even with a commercial system today, is those really ultra reliable low latency communications that for some of the more mission critical, even safety critical cyber physical systems. So this is where I think the SDR would come into play, right? Part of this is because if you look at how the traditional like URLC, like wireline URLC systems was designed, there's actually very rigorous control about the timing behavior, how the schedule works, and even how you implement the TDMA schedule in hardware. And none of those is actually available in wireless systems, right? So there's a lot of innovation that need to be, both system platform, but also algorithmic innovation that need to take place for us to be able to enable predictable safety critical wireless systems. And that actually oftentimes requires us to actually change the current protocol stack, both UE and base station side. So this is where the OpenAirInterface come into play and the SDR come into play. Given the time constraint, I think I'm going to skip a lot of technical details here, but one of the core questions here is actually, how do we bring structure and predictability in inherently dynamic wireless systems? To support this investigation, we have an indoor testbed that has been kind of tested with the OpenAirInterface plus other open source platforms at the core and also ORAN platform. Also, with help from colleagues here, we were able to actually get this working in field in a robust manner in I think 1 or 2 months ago. Now it's fully operational in the outdoor deployment that has, as we speak today, have about 7 base stations and pretty soon close to 35 UEs that can support experimentation with OpenAirInterface and access network. And then for the ORAN, like also the core network, that's where you have a little bit more option, including the OAI core, of course. So some of the specific experiments we're actually running using the SDR and open source deployment is to look at the question of how can we potentially enable predictable control of port packet reliability by controlling the receiver side distribution of interference, and also adapt the transmission power on the fly so that you can guarantee port packet SINR. So on the basis of that, then you can actually look at the question of how can we enable precision control of each packet transmission. One example problem we looked at is the question of, suppose, how to ensure real-time, probabilistic real-time communication requirement like this, right? Give a communication link, you want to transmit packet every such interval with a deadline guarantee and probabilistic guarantee there under the condition of certain port packet reliability. So there are actually mechanisms that can transform this probabilistic control problem into a more deterministic solutions that we have been able to look at. So we don't have time to dive into the details. So we have a demo that's being planned. Actually, we will be able to show share with you tonight, probably this late afternoon, for folks interested, see how the OpenAirInterface works in the field and how some of these early stage experiment executed in ERA. We'd love to see you over there. So I guess let me leave with you one challenge. I think the question, as I was talking to some colleagues here, is how do we build production-ready open source wireless systems, right, for rural broadband, for agriculture applications, and also even potentially for safety critical systems. I know it's going to take us some effort, but we'd love to see if, for folks interested in this, to work together to hopefully bring this to life through, maybe could be first through ERA, but also go, beyond it from there. With that, thank you.
Thank you very much for your presentation. Is there any question? So we have time for 1 or 2 questions. Yeah, go ahead, L'Oreal.
I'm just curious about that Skylark Pharos massive MIMO base station that you have there. What technology are you using with that? Is that 5G as well?
So as of today, it's more for a proprietary solution. It's not compliant with standards yet. They are pushing toward ORAN compliance. So what's available today for Skylark is that there's actually open APIs that we expose to researchers so that you can do fine-grained channel measurement. You can also do like beamforming control, user grouping control. In terms of what the API enables, I think it's somewhere in between the open source and the ORAN. Basically, give you a little bit more control than what ORAN offers. But yeah.
Okay. Thanks.
Yeah. Thank you.
Thank you very much. We are looking forward to see the demo. So I think there we can ask more questions, I guess.